Okay, so today we're going to cover a concept you've probably heard a little bit about, IoT, which is Internet of Things. And that is basically the concept is taking our stuff that is not computers and networking it to our computers to get more functionality out of it. So, first off, this is not going to be one of those, step-by-step examples. Type this in the code, type this in, hook this wire to this pin. We're not going to go step-by-step to it. What this is going to do is talk about the parts you need and the logic of how they go together. So all the stuff will be in this video, but it's not going to be something you can copy and paste the code from. We're not even going to look at all the code. We're just going to talk about what parts are there and what it's doing. And then, so the logic is there, so you'll be able to make it. But if you want to copy and paste, there's no shortage of those tutorials out there. This is more the logic of this is what needs to happen. So the programs that you need to construct in order to do it. So first thing is some sort of device to control things. I have an assortment here to look at. So starting back here, you'll hear both phrases SoC or SBC. The original term was SoC, System on Chip, and at some point people have kind of abbreviated that and started calling it SBC, Single Board Computer. So for an example of that, here I have the Raspberry Pi 4B. This is a full system. It's a full computer system. It just happens to have all these GPIO, general purpose in out pins, so that we can control devices. And as a full system, it runs Linux. It's a Linux system, but as a full system, you need the rest of it, right? You need a screen, some sort of screen, a monitor, a keyboard, a mouse, all that stuff to control it. And some people really like those. Personally, that's why I never use that, because I don't want all that stuff unless I need it. So I'm more of a minimalist. I like to go with the microcontrollers, so that I can build up just the system I need, so that if I don't need a monitor, I don't include one. If I do need some sort of output going to a screen, I include a screen, or a mouse control, or a keyboard if I need one, and just only build the pieces I need. So I prefer the microcontrollers myself, but logically, just something to control it. This is a Linux one, but there's also Windows 10 ones. Latte Panda is a very popular SBC that runs Windows 10 if you're more comfortable with that. NVIDIA has some really nice ones. Some of the NVIDIA ones have AI support fully integrated already, so very powerful SBCs. But microcontrollers, so assortment here. This one we're going to talk about a lot, so we'll get to that in a second. Just single dev board. I just thought I'd go ahead and bring that out because we're going to talk about it a lot. But some Arduinos, an Uno and a Nano. These are cheap Chinese knockoffs. They've gotten very cheap. They're not the actual Italian ones, but they've gotten very cheap, like disposably cheap. So the Nano here, this was in my last order. I believe there was 15 of them. And it was about 8 cents less than I paid for this at a gas station. So that's disposable. STM32s, these are just a couple bucks a piece. They're very powerful. A whole lot more powerful than an Arduino. Just a couple bucks a piece. So good becoming very popular microcontrollers. This one here is probably the most powerful out here. Teensy LC, so the smallest version of Teensy. Teensies are American made, so that adds to the cost right there, and it's very high quality, that adds to the cost, so not a cheap one there. And the other thing you might notice about this is I think most of the examples in the playlist were using the Nano, and this looks a little bit different than the ones in those examples, right? There's no pins connected, and I always order, if I can, I like to order the ones without pins, so then I can put in the pins myself as I need them, right? So like the regular male header pins, this is what was in all the examples. just stick those, go ahead and solder those in there, and then plug that straight in the breadboard. I like to have options as well. You know, maybe the bent header pins, so it comes out at an angle. You know, at the cost of a disposable lighter, don't mind burning up one of those in a case for a project and just go ahead and burn through it. You know, mount that in the bottom of the case with those coming out. Or a similar thing with female header pins instead. Maybe plug wires into that, if I can get that to go in the hole, yeah. And have that option. Or one that I often like to do for testing is these that have female pins on one side and the male pins extend quite a ways. So then I can kind of solder those in, and the male ends on the bottom can stick in the breadboard and access them from the breadboard, or the female ends in the top, access them from the top that way. It's very useful for mocking up designs. So just an assortment of microcontrollers here and an SBC, but that's the first piece you'll need, is something to control it. You just have to, there's lots and lots of options. Arduinos are classics, very cheap, and every single one of these, I use the Arduino IDE to program it. Every once in a while I'll use something different for the more powerful ones, but usually I use the Arduino IDE to program all of the microcontrollers anyway. So step one is find some sort of control device, whether a microcontroller or SBC. So once you pick a controller, the next thing we need is a way to communicate. So I'm going to move some of these out of the way. I'll just leave the Arduino there. That'll work. So, well, I'll leave the Teensy there. Nice, powerful, American-made controller. Teensies are really nice. They're certainly not the cheapest one. But once you have a controller, we need a way to communicate with our devices. So we have a lot of options, right? If we're standing close to it, we can communicate through Bluetooth. So here's HC05. I'll just already talked about microcontrollers. I'll move those out of the way. So an HC05 Bluetooth chip, if we're near our device, Bluetooth is going to work great. But maybe we're not so close to our device, right? Though a device most of us are close to is going to be our cell phones, right? So hopefully I can do this without opening the pack. Okay, it looks like it showed up there. This is my last one. These are very expensive. This was kind of expensive, so I don't want to open the pack. But here's the Gsm module. That's going to be all of our cellular stuff. So we can do SMS and just control it through control our kitchen devices through text messages or voice commands running over the cell network. And just like any cell phone, it's on the back, can't see it without opening the packages, but it needs a SIM card and service and all that to do that. So that's another option. Just tie it into the cell network. That's getting a big glare. There, not so glary there. And so that's a common one. But the one that we're going to talk about today is just regular old internet, a Wi-Fi connection. So here is a popular Wi-Fi chip. ESP8266. In particular, this is the chip's the ESP8266, and this is the O1 module. This one happens to have two GPIO pins itself, which if you look at those pins, if you can kind of see, that's not very breadboard friendly. So for one of these, we can hook, I made this little adapter here, just run some, stick this in here, and then since it's not breadboard friendly on its own, stick that in there and then redirected all of the stuff over to pins here just to be breadboard friendly. So you need to make an adapter, and then that'll work with any of them, right? Whether a Nano, STM32, Raspberry Pi, we can just connect to that whatever controller we're using with this little Wi-Fi module. But, excuse me there. But like I said, this already has one GPIO pin. So people took that idea and ran with it. And that's what this other microcontroller I didn't really talk about was. So again, an ESP8266 chip, only this one, instead of 2 GPIO pins, this one has a whole bunch of GPIO pins like a regular microcontroller. So that's the one we're going to look at today for the example. It is a little microcontroller, which when we say microcontroller, we're really only talking about the chip. Everything else here is just some connections that engineers anticipated we would need. So they went ahead and put them on a PCB with a few connections so that we could use them and not have to wire up the chip itself every time ourselves. So that's what this is. Typically we call them dev boards, development board. It's not much shorter there, but a dev board is the chip already connected to a bunch of pins that we'll need. This one, very breadboard friendly, plugs right in the breadboard, can make all our connections that way. And for the example today, we're just going to use this to turn on and off an LED across the internet. Because if we can turn on and off an LED, we can turn on and off anything, right? That's just providing power to some device, and an LED provides a nice, clean, simple example of that. Right? It covers all the stuff we need for turning it on and off, or sending different levels through pulse width modulation across the internet. And there's only a couple, the wire coming to the LED and the wire going back to ground, so the circuit doesn't look complicated. And there's not so much not a whole lot of extra stuff in the code, but again, the core concept there, if we can turn on and off an LED, we can turn on and off anything. So that's what we're going to look at. This board here's good, but again, lots of options of how we control our devices. So that's the second thing we need, is some sort of way to communicate between our devices. And our standards are going to be the cell service, GMS module, so we can send SMS text messages to our devices and control it that way. Or we can control it through Bluetooth. Or we can control it through Wi-Fi. Whichever option. So for the example today, we're going to talk about Wi-Fi, but any of them, the core logic is the same. We just send our instructions back and forth across a wireless network. Okay, so real quick here, just going to kind of map out the logic of what needs to happen, the way the data needs to flow in order to control some device. Back to that the core idea, IoT, Internet of Things. We want to control our devices, connect our things that aren't computers to the things that are computers to get more functionality out. So we have some sort of device that we want to control. And a point I often express in classes is you're going to need some sort of planning method, even if it's all in your head, jotted down, super organized, some sort of planning method. What I do is kind of make a mess. I'll have some paper sitting out, and I'll jot down notes as I pace around and think about it. Like, I'm pacing around thinking about it, so I just walk up to the paper and write an idea down, and things aren't even all oriented the same way on the page. It's just a mess of notes when I start getting there. I've kind of found that's helpful for me because what's a good way to say it? It seems like as I reorient the page to read all the notes messily jotted down, my brain somehow stored other information in that turning the page around, which way those words were oriented. So that's what works best for me. It's a mess. So I'm going to draw a nice clean map here, but you want to experiment around and find what works best for you. Maybe it does work best if it's all in your head. Maybe you need a nice, clean, systematic method. You have half a notebook filled up with super organized things, super detailed pictures, diagrams, or maybe you just make a mess with this stuff like I do. Or just dive in and randomly do stuff till you find something that works. Probably not the best method, but whatever works best for you, you want to find that. So I'm going to draw a nice clean map here to organize this. Now, some sort of device we want to control, right? For our example, to keep the circuit looking nice and clean, just an LED. It's not a lot of extra stuff in the code that way. And if we can turn on and off an LED across the internet, we can turn on and off anything across the internet. It's just, that's a simple example to discuss the logic. But, some device you want to control, like maybe you're at the grocery store and want to be able to pull out your phone and check a weight sensor in your refrigerator to determine how much milk you have left to see if you need more milk or not. Maybe you had a hard day at work and want to go ahead and start the coffee maker as you leave the office. That way there's a fresh cup waiting on you at home. It's, some sort of device that you want to control across the internet. For our example, just an LED, but conceptually it's still the same. We're just passing control around the world to get back to the device we want it to be. So what do we need? Well, I'm talking about the internet, so we're going to need a web page, right? Web page. And that'll have our controls. A bunch of buttons we can click, some spots to enter words, to give precise commands to the device, some sort of web page that we can access from our devices to control this. Or a phone app or something, but some sort of access. Just going to use a web page for the example here. And along with that web page, we need a bunch of data. So we're also going to need some sort of database. I didn't leave my dream, I'll put DB, some sort of database. And that's connected to the web page. Have information flowing back and forth between our web page and the database. When we push a button, some table in the database updates and says that particular whatever corresponds to that row on the device is now on or off or whatever. But we have a flow of data there, which means we also need that same flow of data here. Our device needs to communicate to the same database. The device is a machine. It doesn't. The web page is just to make it friendly for humans, a nice organized format so that humans can tell what's going on. The device doesn't need that. So we can just send the data straight to the device, send that same data straight to a web page, and that's good for the humans. The raw data is good for the device. The database just organizes all of it. So this is kind of the idea of what we need to control a device across the internet. Database handles most of it. We make it look nice for the person, and we connect it to the device. And that's kind of all we'll need for this. So let's go over to screencast and start looking at these pieces. To begin with, these two pieces, and then we'll look at that one and see the example going. Okay, so to get this going, like I said, need a database and a web page. So I like to test things locally and then just upload it to a web host in one big swoop. So on my local machine, I have Gsm, which is a virtual server running. I have an Apache server and a MySQL server running on the local machine. So to access those, I can just open this up and go to localhost, and then I put everything under my pages. And right down here is the one we need, ESP8266-12E. So that's the dev module. And this page does not look like much. I made a point when I was talking about the mapping to make it look nice, but this is kind of my starting point. So instead of starting from scratch every time, I can have a base set up, and then I can just customize that base for a particular project. Add in better names and things like that. But basically what's going on here is some buttons to turn on and off the pins, or turn on and off whatever is connected to the pins. Just the on-off signals or the pulse width modulation signals. I'm not going to use it in today's example, but maybe some text controls. So set up some words to control it. So you can pass things like LED on and turn it on that way instead of just clicking the button for that pin. But not using that today. And then some sort of display for things coming back, which the default one, this is just kind of my starting point, and then it gets customized for general projects, just has information feeding back from the database. So yeah, so here you can see starts off, everything's off, the text commands, it's holding something, and then once the device retrieves it, that changes to sent. That way, don't repeatedly run the same command. It's going to check and see if it's already ran it or not. Then some stuff coming back. There's nothing in this example, so there's not really anything in those tables. Just created them, and that was it. And then I have this, which this table just has one row. It creates a random number. Every time the machine accesses it, it just changes this value and then updates the time, updates a timestamp every time something in this table changes. And that just gives a way to tell when the last time the device accessed the machine was. So this is my starting point. I can turn a couple of these on. Oh, and then just echo back the word success if things work. So just on and off, and green and red to indicate those, or send pulse width modulation signals. And not every pin is PWM enabled. So if I click one that doesn't have it, say D3 here, it just pops up a message. Oh, that's supposed to say D3. I'll have to change that later. But if I send PWM to D5, that has it on this module. So some buttons to turn things on and off, and color coding to tell what's on and off. And that's my starting point. I just kind of build it up from that. So if I update this, you can see now it says pin 0's on, pin 2 has a 1, pin 5 has a 116, and then the lights. So pin 0, pin D2, and pin D5. So that's kind of the idea. Obviously, for final versions of projects, you probably want it to look a little bit better than that, but that's kind of the idea. So let's look at the code for what's put in for this web page and the database. And I guess I should say website instead of page, because there's only one page, but here's the files for that. There's a whole lot of files running. It's just the human only sees one of them. Most of them are for the device. So let's take a look at those real quick. Okay, so let's quickly go over some of what's on the website here, I guess. Opening that with a text editor. So most of it's PHP. I guess start here. Obviously, there's some HTML and CSS. One thing to note, if for anyone that has me for the class, in class I'll show you what's probably considered the more proper way to do this, using forms to send information to the server. Personally, I don't like to use forms because if you submit a form, it reloads the page. So any information, kind of like here, this slider is currently set to 116. So if I submitted that through a form, it would reload the page and set that back to the default value of 0. So I prefer to just use Ajax and regular HTML tags and not use the form. That way I don't have to reload the page. So that's a big part of what's going on here, but it would work the same either way. You could just use a form if that's what you prefer and just constantly reload the page. Then obviously there's some CSS here somewhere. Don't really need to look at that. There it is. Obviously the style is going to come with a particular instance, not the default starting point. But I went ahead and included some in the default start. Let's see, the JavaScript, most of it's going to happen here. I guess we can look at this. So it's mostly done through Ajax. So set up some variables to hold values. And it's an open type language, so you can put the Booleans in there, or a number, or switch to a string. And in an open type language, we can change what type of data is stored in that variable. So that makes it kind of nice in Ajax here. And what this does is it opens a request to the server, creates a request to the server. In this case, this file tx, which is the standard abbreviation for transmit. So the transmit boolean.php file. And the server is going to respond with numerical codes. And when that numerical code for the ready state is 4, that means it's ready to transmit. And 200 means everything's good to go. The server has a whole lot of codes. Most people are probably familiar with 400 codes, like 404. That's the page not found code. But some sort of code is going to come back, and hopefully it's a 200, meaning everything's okay. And at that point, there's a payload coming back from the server. So we'll take that payload and just put it into a variable. And after that, just kind of parse through it and look for integers. So that's the main basic idea of Ajax is we send a request to the server. It brings back it sends back some sort of payload response, and then we can do stuff with what's in that payload. And instead of reloading the page like we would from submitting a form, we call stuff like this where we just change a particular HTML element. And that way only one element changes, a slight change on the page without reloading the whole thing. So if stuff like this slider is set something other than the default value, it won't go back to the default value every time we click a button. So doing most of it through Ajax there. And that's what's in the JavaScript, and a whole bunch of switch cases and if-else statements basically is what's going on here, just to determine what to do with that information. And again, just a starting point, so that way you don't have to retype the start every time. I can just customize this into the particular project. Next up here is the database. Let's look at it over here first. Come back over to the browser. And again, I was just test everything on a local virtual server and then upload it to a web host all at once. So if I go to the Mysql database running locally, so you can see I have a lot of databases on here. Actually, I probably need to delete those because I'm pretty sure every one of those has been uploaded to a website somewhere. So the idea here is I have 4 tables. I use 4 tables. So one of them is just values to be sent to a pin. The control values to go to the pin, which pin it is, the name of the pin, and that can be customized for particular instances, but basically just what value is going to be sent to what pin. Then this one, since I'm using Ajax on the web page only loads once when you go to the page. So that'll show up in the access time, and then any other access is going to come from the device, the IoT device. So this table, which only has one row, only ever has one row, just tells the last time that an IoT device accessed the database. So basically when the last command was ran, a way to check that. Sensor data isn't being used in our example, but information coming back from the device. So we'll talk about that in a moment. The device can send information back to the server, back to the database as well, and not just read from the database. And the final table is a lot like another control one, not being used in our example here, so I just kind of created the table with text commands. So in actual examples, this would probably be used more than the Boolean controls. So text commands, so you could say things like coffee maker to turn on your coffee maker for that example I keep referring to, or thermostat 73 to change the temperature on your thermostat, and some sort of string-based command rather than just numerical values being passed back and forth, which is much more useful in a particular example. But for a stripped down example, just a lot of Boolean values here going back and forth. So that's what the database looks like, and then a bunch of SQL code to recreate that database, to go ahead and create that database the same every time. So test it locally, and then that way I can just upload this to the web host and recreate this database over there. So that's all that's going on in that one. So now on to the server-side scripts. So the first one up here is the receive. So bringing back sensor data. As we go through here, this first line, it's a good idea to put the connection details in a file, and that way you only have to type them once instead of in every single PHP file. When this goes to the web host site, they'll give me a username and a database name and all that particular for their site, and you don't want to type it in come back and type it in every single file, so that just gets typed once and then refer to that file. I typed in an example. I'm just going to show that instead. So basically, it's expecting data to be included in the URL that calls this file. And then, personally, I like to use the generic PHP database object instead of the MySQL objects, because the PDO works with any database, not just MySQL. So I could just change this to, like, say, a SQL Server, a couple small syntax changes, and reuse this code no matter what type of database I'm using. So I prefer this one. But then it just takes that stuff that was included in the URL and throws that into a query to stick it in the database. And to do that in a URL, how that works, if we come over here and go ahead and close this, and so here's the site it's on basically. So I'm going to copy that. And if I scroll down here, and update. So right now we can see the input table has just this generic analog input, nothing, and a status of null. So if we access that file, so this domain and then rx underscores, delete all that, sensor.php, didn't want all that stuff to pop up. So the file we want to access, but then we want to add some stuff to that file. So to add some information, we include a question mark. That's going to keep popping up on me, I guess. And I always think of that as like a hook. So we're going to hook some stuff onto this URL. And what are we going to hook on? So an input ID equal to A0. So the input ID, we want the value A0 and a status of, well, by default it's null. So I'm going to change that to, say, good. That way we can see it change. So when we basically go enter this URL, like we would if we were going to a page, it's going to take this data, feed it into this PHP script, which then creates a query and updates the database. So that's how the machine updates the database. It just sends a URL with some extra data attached to it. So when we go to that, return success. So if I come back over here and update the display again, you can see the status changed to say good. So that's how the IoT device will update the database, and then once the database has been updated, you can just use Ajax to update some sort of output, probably something that looks better than a generic table. The next PHP file, so there's the receive. So here's the connection detail ones. Just it's running on localhost, still the default username and password for MySQL, but when I upload that to a web host, they'll give me, whatever the host name is, a particular name for the database, and a username, and then a password. This is probably a much more secure password than the default MySQL one of an empty string. So then that only has to be updated once. Then for the Boolean controls, this is just updating the database basically. In the JavaScript file, I was passing in an entire query that was needed, a whole bunch of if-else statements to determine what query to pass in, then just pass that all in at once. Same thing here. This is the update display. I guess what's showing over here right now. It just selects everything from a table and then echoes back some HTML tags and the data from that table. What's next? Oh, so transmit. We're not using the command one. I'll just go ahead and close that one. The transmit Boolean, again, just check the connection details to make a connection. I prefer the PDO objects, PHP database object, because it works with any database. I can just change the MySQL here to whatever type of database I'm using, and then maybe some slight changes to the SQL statements. It's like obviously this one wouldn't need changed at all. A select all query is always the same no matter what database we're using. And then just echoes back some information. So what that looks like, if we come over here, I have this page, so I think it's still on the clipboard if I hit paste. So there's that. And then this was the transmit boolean.php. So when I request that file, so this is what the IoT device will need. It just needs this URL right here to go to that file, and then it gets back this information. And, well, if we look at the code, you can see there's no tags or anything. It's just sending a string straight back. This is the format I chose. You might be wondering why I didn't use JSON. And in a lot of examples, probably would use JSON. I chose this for the default version just as a reminder, almost just as a reminder that it needs changed. It's an easy one to parse through. Typically use JSON or XML, the standard ways to transfer data, or if it's something that needs to be secure. If it needs to be secure, I like to come up with my own protocol to transfer the data, just for one more step that somebody would have to go through to decrypt the data. If it's a standard format, if they know the data is in JSON, they're already one step towards decrypting it. So I just like to come up with my own protocol if it needs to be something secure, and this is what I put in the default one. An easy one to parse through that is more than anything just a reminder that it needs changed. In most cases, it's probably just going to be JSON because that's a nice standard format that's easy to work with, and a whole lot of software is already set up to accept JSON or XML. Either one of those would probably take care of 95% of it, and then I like to do something custom if it needs to be secure. But this is the data that will go back to the machine. It doesn't need any formatting or anything, just a string to parse through. And yeah, we'll look at that here in just a moment, how the machine parses through that. And then, so that's the web page part. Then this last one is like the other control. The user types something in the web page, and then a bunch of if statements in the JavaScript build up a string for the query, and then it just passes that in all at once. So that's the web page part, and then all that remains is the code. So we'll look at that, and I will go find a free hosting site to put this on for the example. The one I normally use, it has cookies, so it has to have JavaScript, which isn't difficult to put in the code, to hard code in the controller, but it does add another layer of complexity, so it's definitely not simplest case example. So I'm going to go find a free hosting site where I can put this website on that doesn't involve cookies, and then we'll look at the code and see this in action. And here is the same thing we just looked at on my local virtual server, moved over to a free hosting site online. I just set up this web page real quick here at 000webhost.com. Free hosting. This isn't the one I normally use for free hosting sites. The one I normally use requires JavaScript to be enabled, which adds an extra little level of difficulty on the code for the microcontroller, enabling all that. I assume there's cookies, they sell data or something like so many sites do. But yeah, the one I normally use has 400 databases on the free account. You can set up to 400 Mysql databases on the free account, whereas this one only has 3 databases. So I assume they're selling data or something to pay for that other 397 databases that are allowed with the free account. But this site is 000.webhost. It might just be 000.web.com. I should check. 000.webhost.com. It's a free hosting site, just a basic one. They have some decent features. It's kind of reliable. So I just stuck this there, but it's the same thing we just looked at. If I pull up the display, you can see everything's kind of set to the default value. I can turn a couple of these on. All the same stuff's there. I think this one has PWM. Update that, and you can see it updates the database. And the only change that had to be made is that PHP file with the connection details had to be changed over to the username and password and all of that, database name that this host site provided for me instead of just the local one set to default amounts. Otherwise, that's the same thing we just looked at. It's just put on the internet. That way, the signal from my computer is routed somewhere around the world through the internet and back to the microcontroller. The whole point of what this example was doing. So that's just the same thing we looked at, loaded to a free hosting site online. And so a quick pass at the code here, a bunch of libraries that have the objects we'll need. Here's where I ended up putting that database. It's a free hosting site. When I was looking into free hosting sites, there were a couple things I didn't like. That's why I went with the other one, but it is a good one. It's reliable. I haven't really had any problems with the sites being up or anything. And in the case of this stuff,
it doesn't require JavaScript in order to deal with cookies. So it works a lot better for nice clean examples here. So that's the base URL, and then the PHP file to pass the Boolean command, Boolean controls. That'll just be appended onto the end of that. And then this other one, not really using it here, but same thing, the PHP file for the text commands, just appended on the end. And have the LED hooked to pin D5, a digital pin 5, and that one also has pulse width modulation on our ESP8266 12E dev board. So I set that pin to an output, and I turned on the serial monitor to keep track of the information when it comes back. Then just initialize everything. Down here, some setup, contact it. And finally, the core part of it here, which is logically is almost identical to what Ajax is doing for the web page. So some of this, in particular this right here, I just copied this line from that Ajax in the JavaScript and just changed it to the syntax for the Arduino IDE, which was basically just move that casting to the integer, move to the end. And I think everything else is exactly the same as it was. Oh, and then declaring, it's a strictly typed language, so I have to say what it is. But otherwise, the logic's kind of the same. You know, is it a 200 code? Is it 200, which here's a nice put to a word so it makes more sense when we glance at it. And is it ready? So same thing as the Ajax checks, and at that point we just get a string back from it. If ever get a string back from the server, then parse through that, which in this case just look for whatever some part of the payload that represents pin 5, parse the data we need out of it. Then here I just echoed it back to the serial monitor to make sure everything looks right. Then down here actually use it. So if it's a 0, then it's off. If it's a 1, turn it on, and obviously in this case I'm just ignoring the case of pulse width modulation set to 1. PWM of 1 is pretty much off, so I'm just ignoring that one, and I'll go from 2 to 255 instead of 0 to 255 for the PWM. So if it's not a 0 or a 1, the strict on or off, then just assume it's PWM and send that value through. And that's kind of the core of the code. Afterwards, some error messaging, which I just copied from the example. That seemed a quick, easy way to do it. Copied from another example. It seemed a quick, easy way to do it. But that's the core of it, and you'll notice the logic is almost identical as what the Ajax was doing to get that stuff back on the web page. So let's see this in action. Okay, so here it is, everything hooked up. The code has been uploaded. It should be running. And to start off, over here on the screen, we can see on the serial monitor for the IDE, it's set for every 10 seconds, so it should come up here shortly. Okay, so there's the stuff from the database. Everything's off, including pin D5 with the LED hooked to it. And then over on this screen, here's that web page we were talking about, the one that doesn't require JavaScript to be enabled, because that does cause a problem with microcontrollers. It's not a big problem, it's just makes the code a whole lot messier when you have to manually pass in cookies. So it certainly doesn't work for simplest case examples. But here's all my Boolean controls. So if I turn on D5, let's see, let's look over here. The LED is off. Come over here and click D5. So it says it's on. And again, yeah, it's a 10-second delay, but you can see the light came on. And the monitor on the IDE is now showing pin 5 has a value of a 1.
So if we come back over here and test the PWM, somewhere around halfway. So here real quick, you can see about how bright the LED is. Come back over here, turn it to about halfway, set pin D5 for the pulse width modulation, and come back over here, and oh, looks like we're just in time to see it get dimmer. And to accentuate that, I'll turn it down a lot. So here's 35. So if I click that, within 10 seconds we should see it get dim. There it goes. And obviously you could set that to much shorter than 10 seconds. I just took a guess for a simplified example. But filming the video, that seemed a whole lot longer than it did when I was preparing everything. So, and well, might as well go ahead and turn that off, and send the communication across the internet, worldwide communication, so that could be controlled from anywhere in the world. And again, if we can turn on and off an LED, we can turn on and off anything. So the core concept of IoT there. And so that's kind of all there is to it. Most of the work is carried out by the database. Everything's organized nicely in the database, since we have some queries set up, have PHP set up on the internet somewhere to run queries to that database, and either bring it back to the web page where we can format it nicely for a user. Probably a lot nicer than that example I just showed. That was just kind of the starting point. For a particular usage, I'll customize it, make it look a little nicer, but that's the starting point I use. Or the query, PHP can initialize some queries in the database and send that data right to the device, which doesn't need to look nice, it just needs the raw data. And that's kind of all there is to this sort of control. And taking those concepts, we can, well, like I said a couple times in this video, if we can turn on and off an LED across the internet, we can turn on and off anything across the internet. So that's the core logic of how IoT works.